Hello, Engineering Sem 2 students. Get ready to master the concept of particular integrals from your chapter Higher Order Differential Equations of Engineering Semester 2. If you are not able to understand any single concept that I teach you in this video, I promise you to personally tutor you that concept for free. I am the only one on YouTube that will ever do that. Let's get into the video. Now, let us start by understanding what do we mean by particular integrals. Let's say if we have a differential equation in the form f dy is equal to capital X. Remember, capital X is a function of small x. If that's the case, particular integral if is given by particular integral pi is given by 1 upon fd times of capital X. So you just take that fd in the denominator and multiply by capital X. So that's the formula for calculating particular integrals. Now, there are a few notations that I would like to clarify here. Remember that the operator D, capital D, is nothing but the first order derivative operator. So, for example, if I have capital D of fx, this is nothing but first order derivative with respect to x of that function f of x. Okay. If it was capital D square of fx, this is nothing but second order derivative with respect to x of that function f of x, and so on. If it was d to the power n, it would be nth order derivative with respect to x of that function of f of x. If it was 1 upon d of fx, that means reverse of derivative. Remember, reverse of derivative is nothing but integral. So if it was 1 upon d of fx, this would be integration of f of x with respect to x. Okay. If it was 1 upon d square of f of x, okay, remember, you would have to integrate that function f of x two times. Okay. So it's integral of f of x two times with respect to x. Okay. And so on. Okay. I hope that makes sense. That's the meaning of that operator d. D is nothing but derivative and 1 upon d is nothing but integral. There is another operator which is very important to understand, which is 1 upon d minus a of fx. Remember, 1 upon d of fx is nothing but integral of fx. Okay. So even 1 upon d minus a has to be integral of fx. So if I want to define 1 upon d minus a of f of x, it is defined as e to the power ax. So whatever a, if it is minus a, you write e to the power ax, integral of e to the power minus ax into f of x dx. Okay, that's the definition. So if it is minus a over here, if it is minus a over here, that same minus a goes over here, but the opposite sign goes over here. Plus a goes here outside of integral, and minus a goes inside of the integral, and you multiply by fx dx. That's the definition of 1 upon d minus a of fx. All right, if it was 1 upon d plus a, can you guess what would that be? 1 upon d plus a of fx. So you just change the sign. E to the power, if it is minus a over here, it is plus a. So if it is plus a over here, it will be minus ax. Integral of e to the power ax fx dx. Okay. So whatever sign is here, same goes inside the integral, but the opposite stays outside the integral. Okay. That's the definition of 1 upon d plus a of fx dx. I hope that makes sense. Now that we understand the basic definition and meaning of those operators, let's get started with type 1, which is calculating particular integral for an exponential function e to the power ax. Remember, particular integral, which is pi, the way we have defined is 1 upon fd times capital X, where capital X is a function of small x. Okay. There are two cases that we'll look here, which is when denominator is not equal to 0 and denominator is equal to 0. What is denominator? We will look into it. Okay. So case number 1 is when denominator is not equal to 0. If you want to calculate 1 upon fd of e to the power ax, the way you calculate that 1 upon fd e to the power ax, you just substitute the value of that a into that function. Okay. So this is nothing but 1 upon f of a, and just write e to the power ax. One thing you have to remember here, that since f of a is in the denominator, it cannot be 0. So I write f of a is not equal to 0. That is what case 1 is all about, that f of a is not equal to 0, or denominator is not equal to 0. Now what to do if denominator is equal to 0? That is where our case number 2 comes. So let's see how do we calculate that 1 upon fd or particular integral for e to the power ax when the denominator or f of a is equal to 0. If f of a is equal to 0, it's very simple. What you do, instead of writing f of a, just write f dash of a. Okay, instead of f of a, just write f dash of a. So just take derivative of that function and then plug in the value a. Okay. And instead of e to the power ax, just write x into e to the power ax. Okay. So basically just add that x, extra variable x. Okay. Now in this case, you have to remember that now f dash of a is in the denominator. Okay. So since f dash of a is in the denominator, here f dash of a cannot be equal to 0. Okay. So now we have discussed what to do when f of a is equal to 0. Okay. So if f of a is equal to 0, if f of a is equal to 0, you simply take derivative and then plug in the value a and just add one extra variable x. Okay, multiply by x. Okay, now what to do if f dash of a is 0? In this situation, in this case, f dash of a is not equal to 0. Now let's see what to do if even f dash of a is 0. Okay, so if f dash of a is 0, you essentially repeat that process. Okay, so if f dash of a is 0, the way you calculate that particular integral, or 1 upon fd of e to the power ax, instead of f dash of a, now you can just take derivative two times. Okay, and substitute the value a, and instead of writing x, just write x square e to the power ax. Okay, where f double dash of a is not equal to 0. Now what to do if f double dash of a is also 0? If f double dash of a is also 0, you just repeat that process. Instead of taking derivative two times, just take derivative three times. So 1 upon fd of e to the power ax will become, just take derivative three times. Okay, and instead of writing x square, now write x cube. Basically, however times you take derivatives, you just keep multiplying x. Okay, so x cube e to the power ax, where f triple dash of a is not equal to 0, and so on. You can just repeat that process. If you keep on getting zeros in the denominator, keep on taking derivatives, keep on multiplying a variable x, and that's how you will get the final result of the particular integral. Now, this concept is best understood with the help of example. Let's solve few important examples to understand this concept even better. All right, now let's solve this differential equation. D minus 1y is equal to e to the power 3x. Remember, this is in the form f dy is equal to x, okay, where your fd is d minus 1, okay. The way you find the solution of this is cf plus pi, complementary function, plus particular integral. In order to find complementary function, we first write the auxiliary equation. Auxiliary equation of this is always given by fd is equal to 0, okay. Fd is equal to 0 is the auxiliary equation. Therefore, we have d minus 1 is equal to 0. Therefore, we have d is equal to 1. Okay, I hope that makes sense. Now, since they are real and rational values, the complementary function CF is going to be given by C1 into e to the power 1x. Okay, please check out my video on complementary functions. The link is on the top right now in order to understand this better. But whoever have seen my video on complementary function will understand how do I get this step. Okay. So that's the complementary function. Now, in order to get particular integral, we know particular integral is given by, as we discussed, 1 upon fd times of capital X, which is nothing but 1 upon fd is d minus 1 times e to the power times your function e to the power 3x. Okay, e to the power 3x. All right. Now, since this is e to the power ax, in order to find the particular integral of this, you can just substitute that value of a. Okay. So this is the value of a that you can just substitute in that d, function of d. So this is very easy. This will just become 1 over 3 minus 1 into e to the power 3x. So this will be e to the power 3x divided by 2. So that's your particular integral, or pi. Now your solution is going to become y is equal to complementary function plus particular integral. Okay, and complementary function and particular integral we already found. So complementary function is c1 e to the power x plus particular integral is this e to the power 3x divided by 2, and that's your solution, general solution of that differential equation. I hope that makes sense. All right, now let's solve this important example. Let's first convert it in terms of operator d. So we can write this as d cube y minus 4dy is equal to 2 cos hyperbolic square 2x. Okay. Now we can take factor out y from here. So therefore we have d cube minus 4d times y is equal to 2. Okay, remember cos hyperbolic theta, the formula is e to the power 2x plus e to the power minus 2x divided by 2. Okay, that's the formula for cos hyperbolic theta. And there is a whole square. All right, now we can expand this square find the auxiliary equation, complementary function, and all of those fun stuff. Okay, let's get into it. All right. So now first let's find the auxiliary equation. Okay. In order to find complementary function, we'll first have to find auxiliary equation. And auxiliary function is nothing but d cube minus 4d is equal to 0. Auxiliary function is always fd is equal to 0, as we have already discussed a few times now. So therefore, we'll solve the auxiliary equation. Take d factor or common. So you have d square minus 4 is equal to 0. Therefore, we have either d is equal to 0 or d square minus 4 is equal to 0. Therefore, we have d is equal to 0 or d is equal to either plus 2 or d is equal to minus 2 by solving this quadratic. Okay. All right. Now we have three unique rational values. So since we have three unique rational values, we can just say that our complementary function is given by c1 e to the power 0x plus c2 e to the power 2x plus c3 e to the power minus 2x. Okay, that's the complementary function. Okay, it's always the first root, second root, and third root if there are three unique rational values. All right, so that's our complementary function. Now let's find out particular integral or PI. Okay, so in order to find particular integral or PI, what we can do is we can just say PI is 1 upon FD of that capital X. Okay, and that capital X is nothing but this function right here. Okay, so we have Pi is equal to 1 upon, and Fd is nothing but d cube minus 4d, and our x is this part right here. We can actually expand this square, so denominator will become 4. Okay, and the numerator is just a plus b the whole square, so that is going to become e to the power 4x plus 2 e to the power 2x into e to the power minus 2x plus e to the power minus 2x, e to the power minus 4x, e to the power minus 4x. So you just basically apply a plus b the whole square over here, a square plus 2ab plus b square. And this will just become 1 because this is essentially 1 upon 2 to the power, 1 upon e to the power 2x. So this and this will just cancel out each other. And next, what we have here, we can take this 4 constant out of that operator. So that's going to become 1 upon 4, 1 upon d cube minus 4d of e to the power 4x plus 2. We can just write this 1 that is left over here as e to the power 0 plus e to the power minus 4x. Okay, I hope that makes sense. Okay. Now this will become, let's make some space over here. So we have 1 upon 4, 1 upon d cube minus 4d. Now let's give this operator to each of those functions. Okay, so we can give this operator to e to the, let's put a bracket here and give it to e to the power 4x plus we have 2 into 1 upon d cube minus 4d e to the power 0x. This is nothing but 0x. Okay, plus 1 upon d cube minus 4d e to the power minus 4x. Okay, I hope that makes sense so far. What I do is I just give that operator to all of those functions right here, and this 2 is constant, so I can take it out of that operator. So this will become 1 upon 4. Now let's see if we can substitute 4 directly over here. So if we substitute 4, this will become 4 cube, which is 64 minus 16. So we can just, since it is e to the power x, we can just substitute the value right here. If this would have become 0, I would have taken the derivative like we have discussed in the concepts. But since it is not becoming 0, we can just substitute it. So this will just become 1 upon 64 minus 16 e to the power 4x plus 2, and we can just substitute 0 here. Now notice if you substitute 0 here, this is going to become 0. Since it is becoming 0, you'll have to take derivative. Okay, you'll have to take derivative. So this will become, just take derivative of this. Derivative of this will become 3d square minus 4. Okay, and e to the power 0x. So whenever it becomes 0, just take the derivative. Okay, and remember you have to multiply by an extra x. When you take derivative in the denominator, multiply by an extra x plus. Now substitute minus 4 here. So this will become 1 upon, if you put minus 4, so this will become minus 64 and this will become plus 16. Okay. I hope that makes sense. E to the power minus 4x. I hope this is clear that when you take derivative in the denominator, you have to multiply by that x. Okay. Now let us simplify. So we have 1 upon 4. This is 1 upon 48 e to the power 4x plus we have 2 times x, 2x. Now can we substitute 0 here? Yes, we can. We can just substitute 0 here and this will not become 0 anymore. So substitute 0 over here. So this is 0 minus 4. So 1 upon minus 4 into e to the power 0x, which is essentially 1. And we already wrote this x over here. Okay. Plus 1 upon minus 64 plus 16. This is minus 48 e to the power minus 4x. And that is your particular integral. Let's simplify this a little bit. This will just become, you can cancel it out and write 2. And this will just become 1 upon 4 e to the power 4x over 48 minus x by 2. This is just 1, so you can ignore that. Minus 1 upon 48 e to the power minus 4x. And that is your particular integral or PI. Okay. So now that you know particular integral, we know solution is y is equal to CF plus PI. So our solution will become y is equal to CF is, let's just copy that CF so that I don't have to write it again. So I just copy that value of CF. Uh, so I have CF, okay, plus PI. PI, let's copy the value of that PI as well. So we have this value right here. We can just copy and paste it over here. So we have basically found the solution of that differential equation right here. I hope that makes sense. All right, let's solve another example. This is again in the form f dy is equal to x. We just need to convert it in terms of operator d. So we can just write this as 6d square y plus 17dy plus 12y is equal to e to the power minus 3x by 2 plus 2 to the power x. One important thing I want to do here is that 2 to the power x, I want to write it in terms of e to the power something, okay? Remember that a to the power x, I will write a note here, okay? I will write a note here so that we can remember it, okay? Remember that always a to the power x can be written as e to the power x log a, okay? A to the power x is always e to the power x log a. That's the property of log. Okay. If you think about it, that x can just go in the power of a. And since the base is e, both are essentially equal. Okay. So, but just remember that a to the power x is e to the power x log a. So this can just be written as e to the power x log 2. I hope that makes sense. Okay. So I'll write that 2 to the power x as e to the power x log 2. All right. Now let's factor out y. So this will become 6d square plus 17d plus 12 times y is equal to e to the power minus 3x by 2 plus e to the power x log 2. Okay. All right. I hope that that much it makes sense. In order to find complementary function first, let's first find the auxiliary equation. So the auxiliary equation here is 6d square plus 17d plus 12 is equal to 0. All right, I won't spend time in solving that equation, but if you solve this quadratic equation, the values of d that you are going to get is minus 4 by 3 or d is equal to minus 3 by 2. I just use a scientific calculator to solve this quadratic equation. Since these are unique and rational values, my complementary function is given by c1 into e to the power minus 4 by 3x plus c2 into e to the power minus 3 by 2x. Okay, that's the complementary function. Okay, complementary function is essentially just write roots of this equation and write c1 e to the power first root x, c2 e to the power second root of x. Okay, now let's write particular integral. Particular integral is given by 1 upon fd times capital X, which is the function of x in the right side. All right, now fd is again 6d square plus 17d plus 12 times of x, which is e to the power minus 3x by 2 plus e to the power x log 2. Okay, we can actually, since we already know the roots of that equation, we can actually write instead of this, we can actually write 1 upon. So since d is equal to minus 4 by 3, we can say that d plus 4 by 3 is equal to 0. And here we can say d plus 3 by 2 is equal to 0. Okay. Why I'm doing this? Instead of writing this quadratic equation, we can write the factor form of it. So we can write two linear functions or two linear equation expressions. So d plus 4 by 3 and d plus 3 by 2. Okay. What is the advantage of doing this? In case one of the factor turns out to be 0, we can easily substitute at least in the another one. So that process just becomes simple. So whenever you have function of d and you know the roots, just convert it to these forms and just write the product of those, just factor it. Essentially, just factor that equation. I hope that makes sense. Okay. So since we have that now, and then we have e to the power minus 3x by 2 plus e to the power x log 2. All right, now we can split this operator in both of the terms. So we have, just let's make some space over here. So we have 1 upon d plus 4 by 3 times d plus 3 by 2 into e to the power minus 3x by 2 plus 1 upon, just give this operator to the second term as well. So we have d plus 4 by 3, d plus 3 by 2 into e to the power x log 2. All right. Now we can just solve those. Now, in order to solve those, let's see if we can substitute it and get the result. If you substitute this, now since this is e to the power ax, we can just substitute it and see if, so this is minus 3 by 2. Okay, this is e to the power ax where a is minus 3 by 2. If we substitute a is equal to minus 3 by 2 here, this is going to become 0. But at least let's substitute it here and then we'll look at this later. So we have 1 upon, first substitute minus 3 by 2 over here. So minus 3 by 2 plus 4 by 3 into d plus 3 by 2, okay, into e to the power minus 3x by 2, okay, plus. Now we can easily substitute log a, log 2 over here because it's not going to make denominator 0. So we can just substitute log 2. So if we substitute log 2, we have 1 upon log 2 plus 4 by 3 and log 2 plus 3 by 2, okay, because log 2 is our a in this case, okay, this is our a. So we can just substitute that a over here if it's not making the denominator 0. And we have e to the power x log 2. All right. Let's just simplify this a little bit. Since this is making the denominator 0, what we can do is just take the derivative here. Okay. So we have 1 upon, let's just simplify this first. Minus 9 plus 8 is minus 1 by 6. Okay. Minus 1 by 6. And let's just take the derivative of the denominator. Because it's making the denominator 0, we take the derivative of the denominator. Derivative of the denominator with respect to d is just 1. Okay, it's just 1. And then after taking derivative, we have to multiply an extra x in the numerator as we have learned in the concepts. And then we have minus 3x by 2. I hope this is making sense. Okay. Since by directly substituting this minus 3 by 2 here, it is becoming 0. What we do is we take derivative of that d plus 3 by 2 with respect to d. So we get 1. And after taking derivative, we have to multiply an extra x. Okay. And then just write this term as it is, e raised to minus 3x by 2. And plus we have e to the power x log 2, rest everything will remain same. So log 2 plus 4 by 3, log 2 plus 3 by 2. All right. Now this 6 is, which is in the denominator can go in the numerator. So we have this is equal to minus 6x e to the power minus 3x by 2 plus e to the power x log 2 plus log 2 plus 4 by 3 and log 2 plus 3 by 2. That is your particular integral. This function right here is your particular integral. Now that we know CF and PI both, we can just directly say that our solution is y is equal to CF plus particular integral. So just substitute the value of CF and PI, and that's where you get the solution. Okay, I hope that makes sense.